Physicists love numbers. We really do. We trust them more than stories, more than opinions, sometimes more than our own intuition. If a number comes out of an experiment, we feel safe. If an equation balances, we relax. But there is one idea, one number, that makes physicists uncomfortable in a very particular way. That idea is infinity. Most people think infinity just means something very, very big. A huge distance, a massive amount. But that's not what infinity means at all. Infinity doesn't mean large. It means no end. It means you can keep going forever, and nothing ever finishes. Imagine counting 1, 2, 3, 4. There is no last number. No matter how long you count, you can always add one more. That idea seems harmless at first. In mathematics, infinity behaves well enough. It stays on the page. It doesn't argue back. But physics is not mathematics. Physics is about real things, real energy, real measurements, and real things do not like infinity. Here's a simple way to see the problem. Suppose I tell you there are infinite cups of coffee on a table in front of me. Immediately, you know something is wrong. Now suppose I say, fine, I'll remove half of them. How many cups are left? Still infinite. I remove half again. Still infinite. I can keep removing cups forever, and I never reach zero. Nothing changes. That should bother you because in the real world, when you remove things, something must change. Infinity refuses to respond. It ignores actions. And anything that ignores actions is useless for describing reality. This is why physicists don't treat infinity as a deep truth. We treat it as a warning. Richard Feynman was especially clear about this. When infinity shows up in a calculation, it doesn't mean nature is being poetic. It means we've made a mistake. It means we've pushed an idea past the point where it applies. Infinity is not an answer. It's an error message. Historically, this has happened many times. When physicists tried to calculate the energy of an electron by treating it as a tiny point with no size, the equations gave infinite energy. That's not impressive. That's absurd. Nature does not produce infinite energy in a finite object. So the conclusion was not that electrons are infinite, but that the model was wrong. We were asking the wrong question in the wrong way. Infinity sneaks into physics when we make assumptions without noticing. We assume space can be divided forever. We assume time flows smoothly without limit. We assume particles have no size at all. These assumptions feel natural because they're easy. But nature has never promised they are true. So whenever infinity appears, physicists become suspicious. Not because infinity is mysterious, but because it usually marks the place where our understanding stops. It's the edge of the map. And good physicists don't pretend the map is the territory. Once you accept that infinity makes physicists uneasy, the next question almost asks itself, does infinity actually exist in nature? Or is it something we invent because our theories allow it? Nowhere does this question feel more tempting than when we look at space and time. Take space first. When you look out into the night sky, it feels endless. You imagine traveling forward forever, never hitting a wall, never reaching an edge. Our equations are perfectly happy with that idea. They allow an infinite universe. But allowing something is not the same as proving it. Physics does not work by imagination alone. It works by measurement, and we can only measure a finite part of the universe. To understand the difference, imagine an ant walking on the surface of a balloon. From the ant's point of view, it can keep walking without ever finding an edge. No matter how far it goes, there is always more surface ahead. To the ant, the world feels infinite. But we know the surface of the balloon is finite. It just has no boundary. The ant confuses no edge with infinite. Humans may be doing the same thing with the universe. So when someone asks whether space is infinite, the honest answer is simple and unsatisfying. We don't know. The universe could be infinite. It could also be finite in a way that doesn't include edges or walls. Both ideas fit our current observations. Infinity appears not because we've discovered it, but because our measurements run out. Time causes even deeper trouble. If time stretches infinitely into the past, then the present moment becomes difficult to explain. To arrive at today, the universe would have had to pass through an infinite number of moments already. But an infinite sequence cannot be completed step by step. If the past were truly infinite, reaching now would be impossible. And yet, here we are. This doesn't prove time had a beginning, but it shows how quickly infinity creates paradoxes when we treat it as physically real. Modern cosmology suggests time began with the Big Bang. Not because we like beginnings, but because our best equations stop working before that point. Once again, infinity marks the place where our understanding breaks down. What we do know is limited but solid. The universe is expanding. Space and time behave very differently at large scales than they do in everyday life. And every theory we have stops making sense when pushed too far. At those extremes, infinity starts to appear. That pattern is important. Infinity doesn't show up in the middle of physics. It shows up at the edges. It shows up when we extend our ideas beyond the region where they were tested. This suggests that infinity may not be a feature of reality itself, but a sign that our descriptions have gone beyond their usefulness. So when physicists argue about whether the universe is infinite, they are not arguing about facts so much as about the limits of knowledge. Infinity lies precisely where evidence ends. If infinity were just an abstract problem, physicists might tolerate it. But infinity becomes impossible to ignore when we look at the most extreme objects in the universe. Black holes are where our best theories don't just struggle. They fail in a very specific way, and infinity is the reason. According to Einstein's theory of general relativity, gravity is not a force pulling on objects. It is the bending of space and time themselves. Massive objects curve spacetime, and everything else follows those curves. This idea works beautifully. It predicts the motion of planets, the bending of light, and even the existence of black holes. But when we follow Einstein's equations all the way to the center of a black hole, something strange happens. The equations say that matter collapses into a point of zero size and infinite density. Space becomes infinitely curved. Time effectively stops. This place is called a singularity. The word sounds dramatic, but what it really means is that the math has stopped making physical sense. Infinite density does not describe a real object. It describes our ignorance. If you squeeze more and more mass into a smaller and smaller space, density increases. That part makes sense. But when the volume reaches zero and the density becomes infinite, the idea breaks. Nature does not produce physical quantities that cannot be measured, compared, or changed. Infinity cannot be measured. It cannot respond. It tells us nothing. This is why physicists do not believe singularities are real objects sitting inside black holes. We believe they are signs that general relativity is being used outside its domain. The theory works incredibly well as long as spacetime remains smooth. At the center of a black hole, that smoothness assumption collapses and infinity rushes in. The problem becomes even worse when we try to include quantum mechanics. Quantum theory governs the behavior of small things. It is precise, tested, and astonishingly accurate. But when we apply quantum rules to gravity, infinities explode everywhere. Calculations produce endless, uncontrollable infinities that cannot be removed without artificial tricks. This is not a minor technical issue. It is a fundamental incompatibility between two successful theories. Physicists have learned to be suspicious of such situations. When two ideas both work perfectly in their own domains, but produce infinities when combined, it means something deeper is missing. Nature is consistent. Our descriptions are not. This is why black holes are so important. They are not just exotic objects. They are stress tests for human understanding. They force us to confront the limits of our concepts of space, time, and matter. Infinity appears not because black holes are magical, but because we are trying to describe them with tools that were never designed for that job. So infinity, once again, is not telling us what reality is. It is telling us where our language fails. It marks the boundary between what we understand and what we have yet to learn. After seeing infinity appear again and again at the breaking points of physics, it's natural to ask whether infinity belongs to the universe at all, or whether it belongs to us. This is an uncomfortable question because it turns the problem back on the human mind. Humans are very good at extending patterns. If something works here, we assume it works everywhere. If a rule applies now, we assume it applies forever. This habit is useful in daily life, but in physics it can quietly lead us astray. Infinity often enters our theories not because we have observed it, but because we have assumed continuity beyond the reach of evidence. Consider how we think about space. We imagine dividing it into smaller and smaller pieces without end, but we have never observed space at arbitrarily small scales. There may be a smallest unit, a limit beyond which the idea of distance stops making sense. The same is true for time. We experience it as a smooth flow, yet every measurement of time is made using finite processes. The idea that time continues infinitely in both directions may be a convenient extension, not a physical fact. In this sense, infinity may be a placeholder for ignorance. It fills the gap when we do not know how a process ends, so we pretend it does not end at all. This move feels logical, but it is not guaranteed to be true. Nature has surprised us many times by turning smooth ideas into discrete ones. Atoms replace continuous matter. Quanta replace continuous energy. Each time, infinity quietly disappeared from the description. Richard Feynman emphasized that science advances not by certainty, but by doubt. The moment we become comfortable with infinity is the moment we stop asking better questions. Infinity gives the illusion of completeness while hiding missing information. It feels powerful, but it explains nothing by itself. There is also a deeper lesson here about reality. The universe we observe is built from limits, objects of size. Energy comes in packets. Signals travel at finite speed. Causes precede effects within boundaries. These limits are not inconveniences. They are what allow structure, complexity, and stability to exist. Without limits, nothing could form, change, or be distinguished from anything else. From this perspective, infinity is not the foundation of reality. Finiteness is. The fact that things end, that processes stop, that quantities are bounded, is what makes physics possible. Infinity erases detail. Limits create meaning. So when physicists say they dislike infinity, they are not rejecting mystery. They are rejecting false clarity. Infinity appears precisely when our explanations have gone as far as they can go. It is the signpost that says our current ideas have reached their limits, not that nature has reached hers. Seen this way, infinity changes from a grand feature of the universe into a mirror held up to human understanding. It shows us where our concepts fail, where new ideas are needed, and where humility is required. Reality is not obligated to match our expectations, only to remain consistent with itself. The universe is not infinite in the ways we casually imagine. It is deeper than that, structured by limits we are still learning to recognize. And recognizing those limits may be the most honest step toward understanding what reality truly is.